So good afternoon, everybody. So welcome to the third of the webinars we're talking about and giving on the National Satellite Test Facility. This one is going to be is titled about accessing the right size facility. So it's talking about the National Satellite Test Facility as well as our existing facilities. If I try and remind people, we've had previous webinars about the NSTF. The overview we gave in January 22. We had a very infrastructure focused one in March 22. And they're all available on the webinar playlist that we've got. And Madeline should have put something as a link in the chat indicating where they're all available on YouTube if you want to refer to them later. For this one, as I said before, it's about accessing the right size facility. We're going to hear from about our clean rooms that we have in our existing facilities and the NSTF by Giles Case. We're going to hear about the dynamics capabilities we have and will have for the National Satellite Test Facility in our existing facilities, and from Ian and Charlie, and then we'll have Cem will come and talk about the thermal vacuum chambers we have and will have in the National Satellite Test Facility. So just as a reminder of where we are, so we're located at the Harwell campus. There's the aerial shot of the site. Our range of facilities range from the very small, this is just the TVAC chambers, which just shows our capability from the very small size chambers through to the National Satellite Test Facility, large space test chamber here on the right. And we've got three locations that we are have our test facilities in. The first circled spot is the NSTF. The second is the building we call R100. And over to the back at the left is the facilities we call R25, which R25 hosts the chambers from that person to the left. These two chambers are in R100 and this one is in the National Satellite Test Facility. And we've been operating all of these chambers for many decades. These ones are just coming up to commissioning, and this one is going to be commissioned by the end of this year. So for the National Satellite Test Facility overview, I've given this before, but I'll just say it again. It's an integrated facility for satellites up to 7 tons, so it's very much the large scale end of environmental testing. It's got thermal vacuum, vibration, acoustic, electromagnetic, and mass property testing, and it's all as a dedicated test center. It's not that your satellite has to be 7 tons, but the scale of the facility is sized for 7 tons. So if you wanted to bring something a couple of tons, it would definitely fit. In terms of the timeline, so the project is building and is moving all the way to the end of January. We are then going to be starting the transition to operations. And in fact, we've already started that in some cases already for the building aspects. And we'll be transitioning all the way to the late summer, early autumn of 23. The EMC and antenna measurement system, eagle-eyed people will have seen that that slipped a couple of months from when we talked about it before. When you're building big facilities, you do have challenges, and we've had a few challenges with the EMC facility, but it's largely back on track now. The vibration facility should be ready in the summer of this year. All of these bars that I'm showing are from the supplier side. So that's when it gets to the site acceptance test. For the TVAC, the mechanical ground support equipment, which is used to load the TVAC, and Cem will talk a little bit about that. And mass properties, Ian will talk a little bit about that. So broadly, by the autumn of this year and into the early part of 2023, we should have had all the technical equipment handed over. Suppliers should have given us the keys to it, and they've done everything we've asked of them. And then we go through a characterization period to make sure we really truly know how to operate the facilities. And so at some point in the summer of 23, that's when we're expecting people to be able to access the facilities. And just to expand out the characterization period, I've said this before, but I'll say it again. We're going to spend that time, we're going to be very busy during that time of making sure it's safe, it's appropriate. We really have characterized the performance, so we really understand our equipment. As a test center, that's critical. That we've supported the implementation of the standard, which is ECSS QST 2007C, the ESA standard for test centers. We have trained and we've proved the competence of our operational team. And we're going to be doing that by using representative items. Some we've bought and a couple we've borrowed. We're going to be making sure that technical performance envelope is known, it's captured, that all the credible accident scenarios are tested. We'll be pulling everything off, pulling all the plugs out of the wall just in mid-test and making sure what's supposed to happen happens and what's supposed to happen, and things that aren't supposed to happen don't happen. Data recovery is checked under any credible scenario and data capacity is checked. So there's a lot of busy time in that characterization period. In terms of people make a facility like this work. We've had an organogram. I'm not expecting people to read it and see it. I guess the graphic to the right that's just appeared is the explanation of what we've been doing and what we will do. To the left of the dotted line is how we have been hiring people and how they've turned up in terms of staffing numbers across the division. And to the right is the uptick we're going to make. So as I talk now, we're 36. We will be about 46 when we've finished. We have people who have agreed and accepted to come already, and they'll be coming this period. And then we'll be looking for probably half a dozen more people to complement, and then we'll be full. So it's really good progress on people, and it's really important that we've got the people now and have had them for a couple of years to be able to train on our existing systems and get prepared so that we're really ready to operate as a test center. In terms of quality standards, RAL Space has held ISO 9001 since 1999. For ETD, the Environmental Test Division, so any activities that are happening under our testing activities, we implemented EN 9100, an aerospace standard from December 2020, which is an underpinning standard required for the ECSS. And then for ECSS, we're in the audit process for R100, and then NSTF will be added to the scope. And in fact, the audit, the detailed audit is planned for the 8th and 9th of June. So we're really right in the thick of it and making sure all our processes and systems actually will support that accreditation. And we're really proud of our customer feedback that we have. We ask everybody who comes and does a test with us, and we do about 120 campaign tests a year, albeit not at a full satellite level, but at smaller scale. These are our responses. So we get 4.79 stars out of 5 in terms of how would people rate the service we provide. People really would recommend us to others, so 4.88 stars out of 5. And the vast majority of people think that we offer value for money. If you want to access the facilities, and you'll hear more in the coming conversations, we direct everybody through to Sarah Nash and our business development team. We're really happy to discuss any requirements at any stage, early stage response for information or detailed proposal RFQ. Obviously, the more information you can give us, the better quality our response, but we're really happy to be involved early. And if anything we've got doesn't quite match what you need, we are adaptable and interested in thinking about how we might change our facilities to support what you need. So I'm going to stop now. I think that's the last slide I was going to say, and I'm going to hand over to Giles, who will talk a little bit more about clean rooms.
And hello, everybody. Yes, so my name is Giles Case. I work for Fletcher. I look after the underpinning infrastructure, which also includes the clean rooms, which support both the test services and independent access. So let me just swap to a set of slides. So here we go. I'm going to talk about clean rooms on this side in this presentation. So just to recap where we are, Matt did cover this roughly. So we operate clean rooms across 3 buildings. That's the R100 and R114 buildings, which are shown in this image. and a set of buildings which is just off of this image, which are the older style buildings. I've highlighted the R100 building here and the R114 or NSTF building there. So overall, we have about 5,500 square meters of clean rooms across these 3 sites, primarily within the NSTF. So that's this building. We have ISO 6, 8, and 9 clean rooms within this building, but on the upper floor, and we'll cover that shortly. We have ISO 7 clean rooms for our own internal use. And on the ground floor of the R100 building, we have ISO 5 and 6 clean rooms, either associated with our test facilities or available for rental for the community. And just a reinforcement there that some are for facilities, some are our own internal processes, and some can be rented. So I thought I'd quickly recap on the NSTF, the R114 building. So this is what it looks like, a drone eye view. It's a little bit easier to describe what we have using a CAD view, so I shall do so. Again, just to reinforce, these rooms are typically available when using the test facilities. These are for the large satellite level campaigns. We have an incoming airlock. That's an ISO class 9 area with a 26-ton overhead crane. We have the first of our dedicated customer clean rooms. That's clean room 1. That is typically class 8 for cleanliness, but we can actually run it at ISO 6 by just adjusting the way the air conditioning works and changing the dress code. That gives us some flexibility to be able to open up various different payloads where we need a slightly higher cleanliness class. We have the EMC facility, which includes the antenna measurement equipment. That's ISO class 8. We have the main hall that's used to access between all the facilities and can also be used for solar array deployment or similar deployments. We have the dynamics facility, which is ISO class 8. We have the second one of the customer clean rooms. So this one will only run at class 8, and it shares a 10-ton overhead crane with the TVAC preparation clean room. That's also class 8. And then not seen in this image, but at ground floor level next to the TVAC chamber is an EGSE room dedicated to the TVAC facility. That's also ISO class 8. What does that look like? Here's an image, and you will have seen this before with Matt's presentation. You can just see the TVAC chamber on the left. That's the door of it. That's the clean room 2 for customers, and you've got the dynamics hall right down the end there. To the right of this image is the EMC facility and clean room 1. And clean room 1 looks a bit like this. So this is the room that can be run as ISO 8 or ISO 6. Obviously not normally with people wearing hard hats and construction apparel. But we also have our R100 building, which I mentioned. This is an image from back in 2015 when it was still shiny and brand new. For those of you who have visited before, you will note that all of the planting that is now here and the mature hedging that's gradually appearing doesn't exist in this image. So the second floor of this building is primarily our own internal facilities. But I thought I'd quickly run through that to show you the sort of things we also do. So we have a central access corridor. We have a changing room access corridor to allow us access into all the different areas. We have our MLI manufacturing facility. That's based in an ISO 6 clean room, although we run it at ISO 7 for this requirement. We have a precision cleaning facility that does run at ISO 6. We have a set of flexible clean rooms or labs, so they can be run either clean or as labs. They're currently used for our own internal programs. We have an internal harness and PCB assembly and test lab run by our internal imaging systems group. We have our own solder reflow area, so that's for doing printed surface mount printed circuit boards to ESA standards. We have a test area for taking the assembled parts and doing electronic testing on them. We have an area that's used for degolding, because that's a slightly more dirty process from the solder. That's also now got a dedicated printed circuit board cleaning system in there as well. We also have quite an unusual facility, so we do conformal coating in-house, and that's actually based in a clean room in this building. So we're one of the few facilities that has a formal clean room and can maintain the cleanliness when we're spraying conformal coating. And then all the local manufacturing sort of facilities that have a dedicated changing room. And last of all, we actually have a clean set of stairs and a clean lift to allow us to be able to go from the manufacturing side of the facilities on the second floor down to the ground floor, which I shall cover next. So the ground floor, here we go. These are primarily associated, these rooms, with our own internal test facilities, which are also available for use by commercial customers. Also, we have some clean rooms here that can be rented by people. So the area is associated with our big vacuum chambers, known as the STC chambers, so that's space test chambers. We have two of these, Suite A, which is ISO 5 or ISO 6, depending on exactly where you are in the room. Overhead cranes, they're about 250 square meters of floor space. And we have another absolutely, well, very close to identical, one of those next door. We then move back to the small clean rooms. So this is where the access from the second floor comes down to the ground floor. We have our mirrored changing room, corridor and airlock, the same as on the second floor. We have some small vacuum chamber clean rooms. So eventually these will allow access to our small test facilities that Cem runs, and they will move across from the R25 building in time. We have a preparation area clean room. This is ISO class 6 with an overhead crane. It's about 95 square meters, and this is one of the rooms that we can rent out to the community. We also have 3 clean rooms to the east of the building. They're all ISO 5. They're about 85 square meters each. These are also available for rental by the community. And then 2 clean rooms, ISO class 6. One of those has actually got black finishes, sort of more designed towards the optical payload assembly and alignment and anything you need to do there. This is what it looks like. So what you have in the left-hand image is this is the access corridor on the ground floor. You have the small clean rooms moving off on your left-hand side and your right-hand side. And this is your access to the second floor, or down from the second floor in our clean stairwell. When you move into the clean rooms, this is on the left-hand side. This is one of our ISO 5 rooms. And you can see an overhead crane in here. And this is a typical small satellite integration platform in here. And on the right, you can see this is one of our black rooms on the ground floor, or the black room on the ground floor. As far as what we do in all of the rooms, as far as services, they're pretty much similar wherever you go in our facilities. So we have about 90 deployed particle counters across the buildings. We monitor temperature, humidity, pressure, and we display that in the room on screens, and we provide audible and visual alarms. We monitor particle fallout and molecular contamination, as you would expect in the clean rooms, and we have about 80 of these spread across the buildings. Really important in modern teams is communication. So we can provide external links out to the internet from all of our facilities using, depending on the area, either fibre links or copper links. And we provide a standard set of services right across, a set of interfaces and services right across all the clean rooms. They're presented slightly differently depending on where you are, but they're all quite common. So we have high power mains connections, we provide earth connections for grounding, we have compressed air and nitrogen gas, we have a processed gas exhaust extract system, and we have local warnings and displays. So you can see the screens and beacons in the areas to tell you when something's going out of specification. And we would expect to supply, irrespective of which area we're in, clean room garments and consumables associated with that gowning process. We'd expect to launder those garments, and we normally provide ESD benching and chairs within the clean rooms. Other items are for discussion. It depends on your request for quotation or request for information. We can supply additional things or not supply these things. And that's part of our contractual discussions. And just to refresh there, if you want to talk to us about your needs, what we can do to help you meet your clean room requirements, talk to Dr. Sarah Nash, and the communication is there. And that is it from me.
So good afternoon, my name is Ian Horsfall, I'm the Dynamics Group leader. So I'm just going to give you an update on where we are with the Dynamics Group, both in the National Satellite Test Facility and also in our existing facilities. So in terms of the NSTF, our commissioning progress is doing very well. We've finished recruiting staff now. We have 7 staff in post at the moment, and another 2 joining us later in the summer. Who are contracted in, so are in under contract, so we expect them to start then, and that will take us up to our full complement, which should enable us to operate the NSTF in 2 shifts and operate the existing facilities at the same time. Our shaker systems have been delivered, and together with all of the hardware we now need for commissioning. And the big difference between this presentation now and even in January is I can show you top left here a picture of the basement and all the cabling that's gone into place. This is actually the lead through into the vertical shaker and all the cabling going through into there. So that's largely complete now. And the bottom, along the bottom here, again a few months ago, I could show you a CAD drawing of the guided head expander on the vertical system, an adapter plate, and a test mass, we call a dead mass, to load it up for test. I can now show you the head expander actually sat on the floor in the lab waiting to be lowered into the pit and connected up. The adapter plate that will go on top of that head expander or on top of the slip plates, and one of 4 dead masses that we've had made. Each of these is half a ton, and these can be used to load up the shakers and to enable us to move weight round on them and exercise them sufficiently during site acceptance tests and future commissioning processes. The data acquisition system we've had in service now for a few months, and we've been using it in our existing lab so that most of the staff are used to using it now. We've trialed it out, we know how to use it, and that's working very well. So we have a picture up here in top middle of 512 channels of data acquisition system. We've actually bought another 2 64-channel boxes since for use in connected bits of work. So we're happy with those, they're working very well. We have a high-speed video system which was delivered last year, which is primarily to support our shop facilities, but we're also starting to use it as a digital image correlation system. This is effectively a stereo view process where you can look at a surface and image it in 3 dimensions at the frame rate of the cameras to watch vibrations happen, or so we can characterize either test items or our own equipment. And the other thing that we've moved forward on is the mass properties machine. We went to Berlin towards the factory acceptance test a month ago, and I'll show you some pictures of that now. So this is the mass properties machine. So that the sort of hexagonal silver and white area on the base of the machine itself, the rest are test masses. This machine is designed to measure the center of gravity, the moments of inertia, the products of inertia, and the mass of the test item. You sit the test item on top, and it's then very, very gently wobbled so that it sits on air bearings, and it sits and moves backwards and forwards, only about 5 millimeters. And it does that in 5 degrees of freedom. So it rotates and it wobbles in 2 directions as well. It can slide in 2 directions. And this allows us to, the machine to deconvolute those accelerations and work out the mass properties of the test item sat on top. In the test picture here, what you can see is a 3-legged sort of tripod array, which is one of the calibration frames. It's actually a much larger one to the rear right in the background of the shot. And this is massed up to simulate a medium-sized satellite. In this case, the simulation mass is just over 3.5 tons. We have viewed that this is designed to test items up to about 6 tons, but as part of the factory acceptance test, it was actually massed up to 10 tons as an overload check. And what you can basically do is put one of these test frames on, mass it up to match the approximate mass properties of your satellite, and then gauge the exact accuracy or uncertainty of the test in advance. And to give you an idea, we'd expect to take a large satellite, something that's 5 or 6 meters high, 5 or 6 tons, and to measure the center of gravity to within 5 millimeters, to less than 5 millimeters of its true position, which is quite good for a structure that large. I'll show you a video of this machine operating now. With Zoom video rates being the way it is, you've got to look quite carefully. What I'll do is start the video, and we're going to zoom in on this position here, just where the support base of the machine and the moving platform match. And when we zoom in, you may be able to see it's moving backwards and forwards around 5 millimeters. And this is a typical displacement during the test. So the test item sees an acceleration of a very small fraction of 1g during the test, and just sits there and oscillates slightly whilst data is collected and deconvoluted. So I'll start this running now. So the table is set oscillating by actuators inside the machine, and then oscillates for of the order of 10 minutes, which is sufficient to catch enough data. There are several different tests done. There's a 5 degrees of freedom test, a single degree of freedom test, and also some weighing tests done. It's largely automatic, so the satellite is simply bolted on, and then the machine's set running, and an hour or so later, all the data is produced, which is very convenient, very good. The mass property machine itself is portable, and what we intend to do is to move that into the clean room where the satellite is being assembled and integrated, and simply move the satellite across on a crane to do the test. So I'll now show you a picture of some recent work we're doing in our existing facility. So 3 bits of work that we've done in the recent past. So firstly, top left, I just show you at the sort of upper end of things that we do. This is a vibration test using force-limited vibration on the SMILE soft X-ray imager. This is being built by Leicester University and is part of the Earth magnetosphere ionosphere interaction measurement system on satellite. So this is a mass simulator of the imager, which we did imaging, we did vibration tests and also shock tests on. It's at the upper end of the sort of size we would normally use. Although the shakers are capable of carrying quite large, the existing shakers are capable of carrying quite heavy tests, in reality the center of gravity tends to get too high. We typically limited to something of the order of 100 kilograms or less for most of our tests. The 2 pictures on the right are a test done last year on our pyroshock simulator. So the hanging plate you see top in the center of this top right image is a large ringing plate which is struck from the back by a projectile. The test item is tied to the front of it, and you subject it to a particular shock response spectrum which matches the required qualification. So in this case, we tested the thing with an Alba pod pocket cube dispenser, and I put this picture up because that was subsequently launched on the SpaceX Transporter 3 mission earlier this year. In fact, I've been at RAL Space for 3 years. That's the first thing that we've tested and I've seen launched, which is quite nice. Then finally, bottom left, we have just show you a picture of a micro vibration calibration system. So micro vibration is becoming a hot topic because we're putting better and better imaging systems and also things like laser links into quite small satellites, and the jitter levels of that laser or that optical system have become critical. So we need to be able to test the effect of any mechanisms on the satellites, such as reaction wheels. Now, I can't show you what the test is actually of due to our normal confidential of our customers, but in the center of that force table, we have a small test item which is producing micro vibrations, and we can then map those vibrations over a range of over part of the spectrum to look at the level of vibration produced by that and the transmission of that into other parts of the satellite, such as optical payloads. And we have a variety of accelerometers for doing that. That's all I'm going to say for the moment. I'm now going to hand over to Dr. Charly Knight, who is a numerical modeler in my group, who is doing numerical modeling to support the test activities, primarily those taking place in the NSTF. So I'll hand over to Charly now.
Hello. So as Ian said, I'm Dr. Charly Knight, the Dynamics Group Modeler. Prior to coming to RAL, just a little introduction myself, I got my PhD in vibration testing for satellites. Been working with sort of developing the models, the shakers for the NSTF, as well as working on model to support direct field acoustic noise testing, which we will hope to do in the future. So the vertical shaker, basically all of our models been looking at trying to model the full system. So going from the sort of actual sort of shaker, so here we've got support structures as well as a sort of seismic mass. The model is in the bottom. We've actually got some images of the shaker in place. Obviously, these shakers much larger than what we have in our 100, much higher overturning resistance, so we can get much larger satellites on there. One of the key reasons for developing these models is so that we can share them with our customers, and therefore we'll have a good idea of how their test items will act on the actual shakers. Doing the same thing, obviously, with the horizontal shaker, slightly different, but again, involving the seismic block. This is even higher overturning resistance due to the quite large number of sort of bearings that are underneath the slip table, which you can sort of see just in the thing. During our commissioning, which we'll be doing later this year, is when we'll be sort of really going through these models, running the actual shakers, and then comparing the results from those tests to verify the models. Part of our commissioning, we've developing a resonant mass dummy nicknamed the Iron Chicken. This will be used largely for the dynamic commissioning of the shakers, where we'll really sort of be looking at kind of verifying particularly the big overturning moments. We've got a sort of image of the on the right is it sort of the FEM model kind of a test. The image on the left is CAD of the actual sort of part that is currently being manufactured. Large plates are to put on the dead masses so that we can mimic various different configurations with weight distributions. This was kind of designed ideally sort of to mimic properties of a full-size satellite, so that kind of really understanding how the shakers will act when they have something that's large on. Whilst running this through, we'll also kind of gain an understanding of how kind of we'll be running the full-sized vibration test campaign. So moving up from the smaller shaker in R100 to the big shakers in the NSTF. Final thing I've been sort of working on here, acoustic testing. So we're looking at bringing in a direct field acoustic noise testing system in the future. This is for testing of, obviously the launch is quite a loud environment. Traditional way of doing it is to put in a satellite in a reverberant chamber, special room built purely for acoustic testing. Unfortunately, building one of those is very expensive. So we're looking at DFAN, as it's called, which is largely a giant ring of speakers surrounding the ISO under test, and can be done in any large space. Image on the left is from a test that was done a number of years ago at RAL. You've got sort of quite tall sort of stacks of speakers, amplifiers, all of which are driving the noise production using multiple input, multiple output control system, or MIMO. Because this is relatively new concept, we're sort of still making sure that we have our modeling of how the speakers and everything will act with the satellite before testing goes, to make sure that the inputs and the sort of the drivers of what we want the speakers to do are going to be correct, as well as making sure all this, crucially, the control microphones will be all in the right place. And that is me. Thank you very much.
Good afternoon, everyone. I hope you can see my screen. So my name is Cem Omur. So I'm the group leader of the thermal vacuum tests. Today, I'm going to talk about the thermal vacuum testing capabilities of RAL Space. In this picture, you can see the thermal vacuums of RAL Space, which are all at RAL campus, but in different buildings. So including a space test chamber 1, and the ones on the left side of it are located in R25. Whereas STC2 and STC3 are located in R100. The large space test chamber will be in NSTF. So if I started with the updates on LSTC, as you can see in the pictures, all of the thermal zones are installed, thermal conditioning units are installed, pumping skids, including the cryo pumps, turbo pumps, and the roughing pumps are installed. Data acquisition units and the control systems are delivered, and we are now ready for the site acceptance test, which will start in late summer of 2022. On the other hand, 120 DC power supplies received to be used with LSTC. The ASBRI control group are building the racks for the power supplies, and they're also working on the open and the closed loop control of the power supplies. So the ones who attended the first webinar may recall I mentioned in that webinar about the loading trolley, which is for to pull and push the satellite into the chamber and out of the chamber. Today, I'm going to talk about the access platform, which can be used next to the loading trolley, which can be seen by the red color. So it allows us to walk around the satellite, and it allows us to finish the instrumentation. Since it can be used under vacuum and outside of the chamber, it can be used as a support structure for the test harnesses, and it can be also used as a support structure for customer potential test setup. The PDR and the CDR stages has been passed. Now the manufacturing is about to start. So that's a closer look to the access platform. It consists of 3 sections: stairs, bridge section, and the walkways. As you can see, the floor plates have different orientation, which allows variable widths of satellites in between the walkways. The bridge is movable, so we can accommodate different variable of length of satellites. In this picture, you can see a photo of STC2, which is in R100 building. I can say all of its subsystems are installed and tested. The commissioning is almost completed. The first customer test will be in June 22. So we are aiming to be compliant to EN 9100 by the end of this year and to ECSS by February 2023. As I mentioned in my first slide, the other chambers are 25. So space test chamber 1, chamber 2, 5, 6, and the climatic chambers are located in either 6 class level of clean rooms, whereas chamber 7 and chamber 8 are in the machine room. They're not located in the clean rooms, but this comes with an advantage because we have very strict rules, cleanliness rules in our clean rooms for the materials to be used with the tested items, whereas the rules are more relaxed in machine rooms where chamber 7 and chamber 8 are located. So with these test chambers, we do have a considerable testing experience since the beginning of 2000s. I can say an average of 50 thermal vacuum test campaigns are completed each year. We are also involved in larger scale projects throughout the years. So we tested Beagle 2, which was a Mars lander. We also tested spectral photometric imaging receiver for the Herschel Space Observatory. The mid-infrared instrument for James Webb Telescope was tested in our chambers. The sea and land surface temperature radiometer for Sentinel-3 was tested in our chambers, and the spectral investigation of the coronal environment for the solar orbiter was also tested in our chambers. And we are still continuing to test the larger scale of projects like the next generations of SLSTR and the MWS for the method project. So in the following slides, I'm going to talk about the test chambers in R25. Let's start with STC1. So it has 2 cryopumps and 1 turbopump. So this gives us a redundancy in the high vacuum range. You can go up to plus 100 Celsius and go down to minus 180 Celsius along the shrouds. So you can also utilize TQCMs, RGAs, and cold traps with this chamber. Chamber 1 is one of our smallest chamber. So it has no cooling capability. Due to that, we use this chamber for our bakeouts. So it can go up to plus 100 Celsius. Chamber 2 is our oldest chamber. So we have been using this chamber since the beginning of 1960s, but it's the most frequently used chamber due to its capabilities. So it has a shroud knit, by which you can go to minus 180 Celsius, and you can go up to plus 100 Celsius. You can use TQCMs, RGAs, and cold traps with this chamber as well. This is chamber 5. As you can see, there is no thermal shrouds in it, but we can use some mobile thermal frames and mobile thermal plates within the chamber to simulate the thermal conditions. You can go again down to minus 10 to the minus 6 millibars because it has 1 turbopump and 1 cryopump. So this is chamber 6, which is a vertical chamber. The advantage of this chamber, we are using cryocoolers in that, so we can go down to 15 Kelvin with this chamber. You can see chamber 7 in this figure. As I mentioned, this is not in our clean rooms. It's in a machine room, so you can test your development models or maybe less clean items in these chambers. You can go to plus 150 Celsius because there is no paint with the shroud. You can also still use TQCM, RGA, and cold trap if it is needed. So this is our smallest chamber, again, in our machine room. So you can use this chamber for your development models as well. So you can go down to 10 to the minus 5 millibars, and you can still use mobile thermal plates within that. So this is our climatic chamber, so we can provide thermal and humidity testing at atmospheric pressure with this. Its primary use is for the qualification of PCBs, electronic boxes, or the RF equipments. To access these facilities, please contact Dr. Sarah Nash, and for the light touch bits for the small scale projects and the test items, you can also drop an email to RAL Space inquiries at stsc.ac.uk, and you will be asked to fill a request for test form, and we can proceed with the next steps. And I need to underline that we will do our best, and we can make some adaptations to accommodate your test items if needed. Well, that ended my presentation. Now I'm handing over to Sarah Nash.
Thanks, Cem. That was a great overview of all of the huge range of chambers that we have available to us. I think everyone else is going to join, but perhaps just following on from what you've just said there, Cem, you mentioned the request for test form. And obviously what you guys need to see is there's some quite specific points that really helps to capture which of those chambers is going to be the most appropriate for someone's particular testing. Can you just quickly run through what the key bits of information are that we need to be able to assess that?
So if I can share my screen again. So I hope you can see my screen. So this is the flow chart of how we can manage the light bits, I can say. So they need to contact you, first of all, Sarah, and they need to fill a request for test form. And then we're going to start a bid review process. Internally, then a contract is prepared and sent to the customer. And if they're agreed with the contract and if they sign it, they need to fill a booking form. And then we can decide a test date. And we are expecting a test plan or a test procedure from the customer. And the chamber configuration is going to be filled by us, and it's going to be checked by the customer, and it should be mutually agreed by us and the customer. And then we can execute the test, and we can send the data and the test report to the customer. So this explains our test management flow briefly.
Thank you. And the highlights for the request for test form, if you got a summary of that?
Oh, yeah. So I have another slide for that. So in that form, so there are some specific questions. So first of all, we are asking the test date, the test duration, any pretest is required or not, any molecular contamination monitoring is required or not, which clean room class is needed, the size of the item, of course, the mass of the item, the required temperature range, the required type of cooling and heating, is it radiative or conductive heating is expected. So if needed, equipment storage requirements, we're asking, this is also very crucial. And if they need our help, we can also ask the required TVT stuff help during the installation and the preparation of the test. Yeah, so these are the questions to be asked to the customer while filling the request for test form.
Thank you.
Yeah.
Now, you've run through various different test programs that we've done over the years, and as the audience may or may not be aware, we've been doing space here for 60 years. During that time, what do you think has been the most exciting program or the exciting thing that you've tested in the TVAT group, Cem? This might require Giles and his memory to cast back a bit as well.
Yes, I joined RAL Space 3 years ago. But as far as I know from Giles, so I think it was during the Beagle 2 testing, right, Giles? So we had to simulate the Mars environment, which is a CO2 environment at 7 millibar, and the temperature should be around -100 Celsius. I think that was the most exciting and the challenging test.
There was one more complication.
Go ahead.
There was wind inside the chamber. So we had a 10 meter second wind in the chamber at 7 millibar, which is quite a challenge. And we also did a solar simulation at the same time. So we had a one Martian sun solar flux on the lander alongside the wind and all the other parameters. So very challenging and quite unique at the time to have done that.
And quite a combination of different things going on, somewhat different to a more regular in-space environment.
Very much, very much. It did make it very interesting, very interesting.
And I don't know that on the vibration side, Ian, if we've got anything that's quite as exotic as that that's been on the shaker. I know you've had a whole range of different things that have been through over the years, lots of batteries, which of course have been very important to make sure that they're safe once they get launched. And some very high precision instruments, I guess, with some of the different particularly optical payloads that we've launched.
Yeah, I think the again, like Cem, being relatively new to this, the exciting a lot of the bigger payloads before my time here, but I think the James Webb Telescope, the MIRI instrument, is probably the highlight. In fact, our current shaker was bought specifically for the MIRI program more than 10 years ago, and so that was tested here. That was also, I think, the first time we did a force limited vibration as well, and some of the work done on that was actually transferred to work done the last 12 months on the SMILE SXI telescope, where we used essentially the same force measurement system to do it. So I think that's probably the highlight of the vibration campaigns over the years.
And I have to admit, Ian, one of the things that I'm really looking forward to seeing more of from your team is with the high-speed imaging that you're starting to develop, particularly around the shock testing and things like that, and starting to see how that comes together alongside the modelling. I think is really exciting to see come together.
Yes, it's quite good. I think it's unfortunate that because of the nature of the work that we do, there tends to be commercial confidentiality attached to many of the things we do, even in-house stuff, which I mean, the really interesting videos don't get out, but we try our best to get permission to publish them, and we'll do that as we get more use of it.
Well, so hopefully the next webinar that we're going to be running won't be until September, but is actually going to focus on the Dynamics group. So by that time, the commissioning program for the Dynamics environment in NSTF will be well underway. And we're hoping that we'll be able to share some more details with you all about what that's going to look like. But it almost certainly will be a work in progress, as these things always are. But I think that's just about us for today. We're just about out of time. So just to wrap up, the information that you've seen today will all be available on YouTube via the links that were sent through previously. The next edition, as I said, will be in September time. In July, we will be at the Farnborough International Air Show. We will have a stand in Hall 4 in the Space Zone. So do come and see us and have a chat about what you might be interested in testing at that point. And otherwise, please do contact me if you've got any inquiries coming up. And I just want to thank all of the panel for the different talks that you've shared today. And hopefully we will see you all again another time. Thank you.